Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Professors Ron Cole and Wayne Ward from the Center of Spoken Language at the University of Colorado. I've known both of them, I guess, since 1987, since our days at CMU, although Ron left soon after that. And he's been at OGI since then, and now at Colorado. And Wayne also was at CMU back then and went to Colorado. They have a formidable group over there. And for the last, I guess, 5 or 10 years, they've been doing a lot of interesting research in using speech technology to create virtual agents and to do work on child learning and children education. And today they're going to tell us a lot of what they've been doing and how to see if we can learn something about how to use speech in this context and how to create virtual agents. So, Ron?
Thank you very much. It's delightful to be back here. Alex, thank you for sitting directly in front of me. Everyone else in the audience, for some unknown reason, is far to my right. Oh, because the screen's over there. Okay, I've never given a talk before where my whole audience was in the field of vision to my right. Okay, so it's really great to be here. Great to see you again, Alex. I guarantee you that my leaving had nothing to do with your arrival at CMU. Okay, so what we're going to talk about today is virtual humans and the vision and their promise. I'll give you some scientific rationale for their use and for the design of systems that use virtual humans. And therapists will give you demos of the systems we're building. Hopefully they'll all work. And then the first part of the talk, although it starts with a vision, will then describe systems that are actually being used by people today. Approximately 1,000 people in the world are using our systems to learn and to acquire speech skills. Then we'll tell you how the research we're doing in our lab, which is really basic research, is being, how we hope to combine next generation research results with these systems to produce the systems of the future. And as a research lab, what we do is we make proposals, we conceptualize and plan projects, and we send out these proposals. So it's not so far away because the vision we'll give you of the next generation of systems are actually written documents that we sent out to Department of Education, National Institute of Health, and National Science Foundation to try to fund the work we'll describe. And then if we get to it, we'll talk to you about what the technical challenges are. We'll say, here's the technologies that are in the systems now. Here's what they can do. You'll see some of that in the demos. Here's their limitations. And here's the research that we believe is needed to make the visions come true. So we'll start out with the vision of virtual humans. A virtual human is a 3D, although it could be a 2D computer character that has human-like personality, attitudes, and opinions. It's believable. It engages people in natural face-to-face conversational interaction, just like you talk to another person, to produce great communication, learning, or clinical experiences. The promise of virtual humans is that you can provide experiences to people that another human being could provide. And that's an amazing promise because there are literally tens of millions of people that could benefit from better tutoring, from individualized instruction, from language training, second language learning, from therapies of many different kinds. And we know that we can't afford to train enough people and pay enough people to provide the kind of individualized attention that'll provide these benefits. But if you could invent computer systems that behaved exactly like, or even better than, perhaps, these expert teachers and therapists, then you would have 24/7 access, you'd have inexpensive, 100% accessible, and engaging and effective experiences that would present just tremendous benefits. And in addition to just these practical benefits to society, you have amazing research tools. So if you want to do research on the therapeutic process or the learning process or face-to-face communication, you can manipulate virtual humans in ways that are difficult to manipulate people and expensive to manipulate people. So when we talk, we always are gesturing and making eye contact and doing many different kinds of behaviors that are completely unconscious. You'll run an experiment, and after the experiment, the people say, I know you were studying gesture, and I never gestured. And then you look at the videos, and they're going crazy gesturing, right? So you can manipulate these virtual humans, and you can have them behave in certain ways, speak, emote, gesture, do eye contact in response to what they do, and so forth. And you can see what the effects of all those manipulations are. And it's very difficult to do with human stooges. So what's the scientific rationale? What the biggest mistake that we always make is we use our instincts and we design systems, and we think that we know what we're doing. And we all make those mistakes. I continue to make them after 10 years of designing the system. But what we need to recognize is that there is an emerging and profound scientific literature that can motivate the design of these systems. And I'll be able to show you demonstrations that violate some of these principles because we didn't follow them and read the literature in time when we built our systems, and now we have to correct these mistakes we made. What Cliff Nass and Byron Reeves, and this is significant work, in the media equation, Bill Gates wrote an endorsement on the back cover of the book. They have demonstrated through literally dozens of experiments that people interact with computers just like they interact with other people. And the more you can make a computer, and it's just a fundamental thing, we interact with media. We say, oh, our computer stopped talking to our printer. I mean, we always anthropomorphize our artifacts. And what they have shown that if you take knowledge of social psychology, of how people interact with each other, and use that knowledge to design interfaces, then you're going to have more engaging and effective interfaces. So there's a lot that can be learned about design. I'll give you one simple example. If I write something and give it to you to review and then say, okay, what'd you think about it? You'll be very polite. If you were to get that same manuscript and show up at a review panel, you might bash it. You just tend to be very polite face-to-face. Okay? One of the first experiments Reeves and Nass did was they had a program running on a computer, and then they did a survey of what the person thought about the program. And they got a certain result, and the people tended to like the program. If you had the people instead move to another computer and do the survey, they gave much more nasty reviews of the software. It was exactly the same survey, it was just the computer, but the notion of being polite to the entity that gives you the thing held. Okay? And they've just done dozens and dozens of experiments that say that the rules and conventions we use when we interact with people apply to design of interfaces. So we should read those experiments when we design them. There's also the notion that the more you can make the computer take on social agency, the more you can foster social agency by adding voice or by adding voice plus face, the more that you're going to perceive the computer to be another human being. And if you design those interfaces well, then you're more motivated to work with the computer, and you will get better experiences. You believe that the system's more believable, more credible, more likable, and typically you'll get more effective experiences. And lots of experiments show that, and there's literature about this. Some of my favorite research in the area of learning came from early work from Benjamin Bloom, who posed the 2 sigma challenge. Basically, Bloom and his students went into classrooms and gave lectures, and then they gave tests to find out how much people learned from the lectures. And then they had exactly the same content provided in individualized or small group instruction and gave the same test. And if you got a C in the lecture, you'd get an A in the test. Basically, that's the 2 sigma benefit. And that's been demonstrated from 1 to 2 sigma gains almost almost universally, even if you have students tutoring each other, peer tutoring in schools, okay? So there's something about the human factor there and the face-to-face and the individualized attention and the responsiveness that you can give in small groups or individualized instruction. And of course, we expect that if you can design interfaces that have the persona effect, you'll engage with that entity and learn like you're learning with a real person. And then there's a whole set of studies that have been done in Santa Barbara initially with Richard Meyer and his colleagues on how do you design multimedia learning systems. And basically what Meyer does is he'll take problems like how does lightning form, or how do pumps work, or how do brakes work. And he'll give it to you as a text, so you have pictures and you have text on the same page, or he'll give it to you as a set of illustrations while they're being narrated, or they could be narrated by a talking head or just the voice and so forth. And what you learn, he's got this cognitive theory of multimedia learning, and the idea is that auditory and visual channels, you can produce separate mental models. And then you can combine them and you get a richer representation. If you try to put all the information in visually, then you're overloading a limited channel and you don't learn as much. So it's much better to narrate the text, narrate it, give a spoken explanation while the person's looking at the picture, and then you could put some arrows or animation into the picture so they know exactly what they're looking at. And that produces much better learning. Okay? So point of all of this is that there is a whole literature out there from various areas that gives you strong guidelines on how to build these kinds of systems, and we want to bring that knowledge to bear when we build our systems of the future. So now, we're not saying we always do that well. One of the things I didn't mention here, and I don't want to forget to mention, is that when you build systems that have virtual humans, that have lifelike 3D characters that you want to behave like people, then you want to do something called participatory design. So when we build our reading, our learning, and our therapy systems, we work with the experts as well as read the literature, and we say, how do you teach? And we observe how they teach. And then we design the systems with the experts and with the students and the patients that are going to use them. So the experts and the end users and all the other stakeholders are involved in the design of these systems from the initial stages of the project. We plan, we conceptualize, we do prototypes with them, and then we test with the experts and the end users. And that's part of that design process. Okay, so basically to summarize that, the recipe for building a virtual human system is you get informed by the field, then you analyze the performance of highly effective experts, then you develop the system, and then you use end users to test the system. And I'm sure that's exactly how you do it here. You do lots and lots of testing with users all the time. Then you evaluate the system in ways that are done based on medical models. You do formal clinical trials. You do both qualitative and quantitative evaluation. And then you want to try to scale up and sustain it. Now let's go into the world of virtual teachers and therapists and hopefully go into various demos. The last time I was here, I showed you a video of, that was shown from Primetime Thursday of children that are profoundly deaf that had either cochlear implants or hearing aids being taught vocabulary using a talking head. And since we did that last time, I'm just mentioning it, that was sort of the foundational project between 1997 and 2000 that was broadcast in March, the Ides of March 15th, 2001. And now we've moved on to a new generation of virtual humans that you'll see are much more engaging and lifelike, that use natural human voice instead of synthetic speech. So I'm going to now start with the Foundations to Literacy program. This is a comprehensive scientifically based reading program that's designed to teach essentially any child to read and comprehend text through conversational interaction with Marnie, our virtual teacher, and we try to get Marnie to behave like an expert reading tutor.
So Marnie is evolution from Bodhi?
Marnie is one of a dozen 3D models that we use using the CU Animate system, and I'll show you a few of those models in just a minute or two. And Baldi has been withdrawn from the CSLU toolkit and withdrawn from our research environment The CLU toolkit, which I developed at OGI, has been downloaded. It's not like Windows. You know, I can't impress anybody at Microsoft with our number of installations, but there's been about 25,000 installations of this toolkit around the world. It used to have Baldi, and it's been replaced with our animated characters, and people can design interactive dialogue systems using this toolkit. So Baldi used text-to-speech synthesis with Festival, and it was a very unlifelike computer character, but it had very good lips, and it was good for the paired with synthetic speech, which Cliff Nass's research would suggest, because if you have a very unhuman character, then you want to have a synthetic voice because there's a good personality match there. And now we use normal speech because we have more human-like. Marnie, we always record our speech, and I'll show you how we do that. Okay? So all I'm showing you here with the project team is that this was a large project. Overall, grants totaling about $10 million over a course of 5 years, supported a large project team to build these literacy tutors. And I just wanted you to realize that there are a lot of people involved in this, and they all contributed important in different ways. So the first thing about Foundations to Literacy is that it's based on theory and research. There's a lot of theory and research that motivates how you teach children to read. The National Institute of Health, Department of Education, there's like a zeitgeist. There's a certain way that you have to do research these days. Scientifically based reading research is what they call it, where you do interventions and you evaluate them and you see how children respond to the interventions, and then based upon what works and the evidence and so forth, then you can build these systems. The basic theory of reading, which many people subscribe to, is the two-component model, that you have a set of processes for word recognition and you have a set of processes for comprehension, and in fact you can measure them independently. So if I give you tests and flash a bunch of words in front of you and ask you to read each word out loud, I can find a reading level for you, how well you can read words. And if I tell you a story, there's no vision involved, I just narrate a story to you and then ask you questions about how well you comprehend it, that'll measure your comprehension. If you then ask a person to read a text and answer questions, all the significant variance is accounted for by the sum of the two variances from the reading and the comprehension. So people basically say we want to teach reading in terms of word recognition, and we want to teach comprehension. Now, obviously, there's this process where you go from recognizing words to recognizing words in a fluent and expressive way so that you're comprehending well, and that has to be part of the reading program. So that's basically the theory that guides what we do. We built a system called Foundations to Literacy, where we have these things put together. Basically, we have a set of exercises, can you see my cursor here, that are doing these foundational skills. And foundational skills consist of all of the knowledge you need to be able to recognize words. And teaching this means that you're going to teach people letters, and letters in different fonts. And you're going to teach them the names of the letters of the alphabet, and then the sounds of the letters. And then they're going to put the letters together and know what the sounds are and use those to build words. And when they build words, you want them to be spelling words at the same time. There's basically two kinds of words. There's words that are regular, meaning you can decode them according to rules of spelling to sound. And then there's words like through, okay, many of the most common words that are sight words, and you basically have to learn letter patterns. And you teach both of those things, and then as the children acquire the skills, you put them into these interactive books, and depending upon their level, you either narrate books to them and get them the notion of comprehending text and understanding that words follow each other and make meaning and associate with the pictures, and books consist of pages and so forth and so on. And then you start asking them questions, and then as they learn to read the words, you put them into books where they can start to read out loud, and you can give them feedback and test their comprehension. So they go back and forth between reading. And what we do is we initially now test students, assess students' reading level. We don't do this automatically, although we're funded to develop the automatic assessment in our lab, and that's going very well. But right now we give them paper and pencil tests. We see how well the child can read, and then we put them in the program at a particular point in time based on their reading skills, and then the program takes over and everything is automatic from that point in time. And based on where they are, they'll have a set of foundational skills exercises, and they'll have a set of books. And they'll get the illusion of choice, because empowerment is very important, and the children can say, I want to do this exercise, or I want to read this book. And then when they exhaust the exercises, then they move to the next level. And the program takes them at each stage, and I'll show you this, it takes them through discovery, where they learn the concepts, and then it takes them through a timed test where they have to get everything right, or a criterion amount right on the first choice, and then it takes them to speeded tasks in the same exercise, so they learn automaticity, because reading is an unconscious automatic activity. So you teach them, you test them, and then you get them automatic, and in fact we review them a month later or 2 weeks later and make sure they just haven't learned the specific task and that they've generalized their knowledge and so forth and so on. And they go back and forth between the books and these different exercises in the study plan. And then there's a progress graphic that when they come back to the homeroom, they see how well they've done, and they know they're progressing within the program. That's very important for them to have a user model of how they're progressing, where they are, where they're going to. And then when they read books, they go into their library, and there are certain times in the program they can go read books in their library. So that's the concept of the Foundation to Literacy. And you're going to see a set of different exercises or learning games which teach them these different reading skills. So they start with very specific, simple things, and then they learn things like silent E and the controlling R and the fairly sophisticated rules. And then we're going to go into interactive books. Interactive books will read to the student, they'll test comprehension, they teach students to sound out words and read fluently. And I'm going to demonstrate to you the different interactive book features, and you can see how we author books. This here you're asking a question about the sun and the north wind. Say, what did the sun and the north wind want the man to take off? And they can move their mouse around and see the different objects and click on the one and get feedback. Okay, so there's ways to test comprehension. And notice that's a concept question. We didn't say, where's the coat? We said, what did they want them to do? And you can give multiple choice questions. If the child can't read, they can click on the question. They can click on each of the choices, and Marty, or Julie in this case, will read the responses to the child, and then they can choose. So notice that you can have a complete program here that teaches all aspects of reading to the child. And we found that with one session, if the child has never used a computer, where you teach them how to use the mouse, to sit down with them, and stay with them for one session, they can go off and do it. And this is for kids that are immersed in English. About a third of our kids speak Spanish. And they're the ones that are benefiting the most from the program, in fact. So that's the, and we have them in 15 languages now, the ability to read aloud and for the character to speak. So let me give you a demo now. Yes, ma'am?
What is this targeted towards? Towards what age group is this targeted?
You're gonna, I didn't put my hearing aids in for my talk, so Wayne, you're going to have to give me the...
What age group?
Oh, so we start with about 4-year-olds, so early kindergarten, and we go through 2nd grade now. And in fact, a really smart kid can run out of the program at the end of the 1st grade. And what we did is we spent the summer putting in more complicated spelling tasks and more sophisticated content to take the child through about middle 2nd grade now. Okay?
Have you tried it on adult ESL learners?
Which kind?
Adult English as a second language learners?
Oh, yeah. A third of our children are Spanish-speaking children.
No, but have you tried it on adults? Does it make a difference?
Adults.
Adults? No, we do a lot of testing on adults, but we've never put the program in front of adults that are illiterate to teach them to read. And we've had discussions about this. I think it'll work just fine, although they might be a little offended by the childish content. But if they really want to read, they'll probably get past that. I think it'll be a great tool for adults. I would redesign it for the adults for the content, but absolutely, why not? Okay, maybe the instructions could be different and so forth. So I better get on. We have about 100 slides here and some demos. So, and I tend to ramble. Let's, so I gave you, now this is where you all hold your breath and hope that the demos work.
Hope you can find it on the desk.
Okay, so nothing just happened. Let's just see. Okay, so I started the system before. Let me restart it. You're all Windows experts here. What happened to my Internet Explorer?
Oh, you have multiple.
Oh, we'll just try it again. Hopefully I don't have two systems running and it'll screw everything up.
Yeah, you have to use
Is it down there?
just, yeah, one of it, yeah. Okay.
There's another one? Let's see. It says there's two.
Click on that. Just click on that.
But now I'll have two running at the same time, right? So should I kill this and click on it? There it goes. Okay, so I'm going to go into a book. Now this isn't what a child sees. This is a developer interface, and it's mainly used for development and to do demos. So here's Marnie. She's one of our 3D models here. We don't let the children can only go like from here to here. Otherwise they spend all their time spinning Marnie. We found that. And some never get tired of doing that. So Marnie will speak, and she's got wonderful lips. So in this mode here, where it's words a child can be reading, it was the first day of
Summer.
vacation, Sue and
Billy.
And that's a nice assistive technology device, okay? And Marnie can also read whole sentences.
What can we do today? Billy asked.
Now her head moves. Let's go. We have this many characters and a few more that we couldn't fit on here that are some pretty good ones. I want to load in this little program here, which is in all of the books. And now when I have her read,
I don't know about today, but I have an idea for tomorrow, said Sue.
and now she's moving her head. It's just a few simple rules here. One of our research topics that we'll talk about at the end if we have time is how you can use statistical models from data to do a very good job of narrating any text and producing the right head movements and face movements and eyebrow movements and emotions based on the content of the text. That's one of our proposed research.
I saw very few animation, outside that actually can model the tongue-tip movement. I saw that you have tongue.
There's very few that do that. And we just did it with a few simple rules. It's just looking at beginnings of paragraphs, beginnings of sentences, looking at the punctuation and
The tongue.
the tongue. You know, Marnie has a wonderful tongue that reaches all the targets, and my son knows how to show the tongue, and I don't. I forgot how to do it. But I can make her face go transparent, and you can watch the tongue. So that capability is in there if you want to use it for articulation training. But it's there. You'll just have to trust me today.
I'm just saying that the way I saw when the mouth is open, one can
Oh,
see
the
inside
visible tongue,
And that's important.
very good.
It is visible.
Oh, yeah, yeah.
It's-
Oh, yeah, you'll see it in the exercises. Okay, so she can narrate the whole text, which we do when children are just learning.
It was the first day of summer vacation. Sue and Billy were eating breakfast.
And then there's various, when they click the page, when they click to turn the page, various questions will pop up. I'll show you the authoring of all of this in a second. I can select different models. So here's Angelica. And she'll just start talking instead.
What a great idea, said Billy.
And of course, you can record different voices for the different models and so forth. So we have an ethnically diverse cast of characters here. I can usually, I think it's set for male voice now on my demos. And I can start reading. And I go to the beginning, and I say, It was the first day of summer vacation. Sue and Billy were eating breakfast. What can we do today?
Billy
Asked. I don't know about today, but I have an idea for tomorrow, said Sue. We can go to the zoo. But the hippopotamus? Zoo is far away, said Billy. Who will take us? I don't mean the zoo in the city, said Sue. We can make our own zoo in the yard. All our friends can bring their pets. So this actually works quite well, tracking the speech as we read. Could you see the cursor moving under the words?
So it's a real-time segmentation, the voice segmentation.
Everything is happening in real time. This is a real live demo. Okay. I'm going to go here to the edit mode just so you can see. This whole thing is an authoring environment. And we build all of our own books. So everything here is an object, and you can just format everything on the screen. And then you can ask questions and record speech and put images and new text in. If I double-click here, you'll see I'm just in a Word-like editor. And I can change the fonts and underline things and make them bold and so forth and so on. If I want to start recording the text, I just go over here. I can select a utterance.
We can make our own zoo in the yard.
And you can see her say it. Let's do that again.
We can make our own zoo in the yard.
And then you can see that the speech recognizer aligned it word by word and segment by segment. And then I can record it. We can make our own zoo in the yard. And then you align it, and then hopefully she'll say it. We can make our own zoo in the yard. Okay? And that'll work. This is done in a soundproof booth with the right stuff so you don't get all these bursts and so forth. And then this is all our own technology. This is our animation system, CU Animate. And it's a pretty lousy user interface, but we're redesigning it now. I can make her do pretty much anything I want. This is old motion targets. I'll show you the new ones in a few minutes. I can put joy here, and then when I have her speak, she'll get joyful. We can make our own zoo in the yard. And I can do anything. I can make her wink, blink, roll her eyebrows. You can do incredible things and so forth and so on. So this is the authoring tools that let you build these books. And what we'd like to do is reduce authoring as a research project and be able to just provide the text, have a voice talent record the book, and everything is automatic, and the right face movements and so forth. And then, of course, there's going to be a lot of interaction. The child's reading.
Did you modify the speech so that it becomes emotional?
Well,
if you put
the speech is emotional because I can go in and I can say, we can make our own zoo in the yard. Right? And I can do that. Well, now it's all clipped, but you'll get the idea here. We can make our own zoo in the yard. Right? Okay, so emotion, the voice is an incredibly wonderful instrument for emotion. What you'd like to do is take the text and the voice and then automatically produce exactly the right facial expressions and so forth by her and not have to author it. But we can author it now. So you can do it. Okay? So you better let me move forward here. We want to go back here and not.
So Ron, I have a question. You do record the original human voice.
Yeah.
You could also videotape the character if you want.
You could always do videos, but there's tremendous cost with doing video relative to doing 3D models. For one thing, I can just change all these character faces. And there's a lot of research that shows that African American children would rather be taught by an African American teacher. Okay? And this can be done onto your cell phone screen with our CU face. It's MPEG-4 compliant. We can take the parameters. We run in the schools with one server serving 4 schools. And all the client machines, and they're all using the streaming of the parameters. So it's very efficient, where if it was video, you'd have a big channel you're going across, you'd have to cache them into the systems and so forth and so on. So there's just also, let's say I want to change her expression, have her raise an eyebrow here, you have to re-record the videos. So there's a lot of advantages to doing this as a research platform as well as a real-time platform. And we can get into this discussion. But I'm a big fan of these 3D models.
What about, in that same line, what about the possibility of just using the videotape to extract the expression parameters? So like, just getting the facial expression, because I mean, it's much easier to do that from video than
using video to model the...
To extract the facial expressions.
Yeah. I mean, You mean using computer vision as part of the
Exactly.
system?
Yeah.
We'll talk about that at the end.
Okay.
That's in fact a very important thing to do. One of our big research agendas here is to model the virtual ballet that happens when two people talk and establish rapport. And that requires vision, and our system is blind today. Okay? And we want to do that. Okay? We do use video all the time to look at the models and then build good models. Okay? For the motions and the targets and so forth. I'll talk to that. Most of these interruptions are things I'm going to address. All right? So it might be best to make little notes. I don't mind responding to questions, but if you want to be here this afternoon. Okay. So let's get out of this. Let me show you just a few of the kinds of, let's do something like beginning sounds. So we have something like 30 or 40 different foundational skills exercises, each one with different levels, with different stimuli.
Letters and sounds some more.
So I just want
Let's
to
start playing.
give you the concept here.
Make the word pan.
Okay. So what was that?
Pan. Pan.
So I can make her
Pan.
say the word, and now I'm supposed to build the word pan.
An. B.
That sounded right.
Van. Try again. Watch me say pan. Pan. Terrific checking. Let's build the word bad. Bad. Bad.
Okay, so you get the idea. This is the
Pin.
discovery phase. And when they're in the system, after they get several in a row right, they can then elect to take the test, and then it's a time test, and they have to get so many right on the first try, and then you know you've learned it. Okay? And then they move up a level, they get feedback on the progress graphic, and then they move to the next level with a different set of letters, some overlapping and some new letters. And eventually they go to blends, BL and PL and TH and so forth. So you get the concept here, okay? And there's just a whole bunch of these, and we're not going to have time to go through them. Hi, Margaret. When we meet this afternoon, if you want to view more of these exercises, there's matching games. The one thing I will say is when we do something like beginning sounds, there's 4 or 5 complementary and reinforcing exercises that all teach the same concept. So they'll go into like a matching or concentration game, and they're matching pictures with the sound of the letter. Okay? And so there's several things that happen at the same time. I think I'm going to go out of Foundations to Literacy just so we get through to talk. There's many more demos I can do on it. But let's save that for interested parties. We're around later as needed. We're here till about 3:30. Okay, so interesting. There it goes. So the status of this program now is that we're in about 50 Colorado classrooms. We are going into our 3rd or 4th year of deployment in classrooms. And last year, we had very good learning gains in kindergarten, 1st grade. And we gave surveys to teachers. We interviewed teachers periodically through the year. And we gave 120 children an interview, and with pictures and so forth. So we'd say, what does this mean? What happens when this is happening on the screen? Because you want to say, do they know what the feedback means? You know? And we found real bad design things that we thought we were giving kids useful feedback, and they didn't even know what it meant. Okay? And, but the most astounding result was how much these children view the animated character Marnie as a real teacher. We use these Likert scales, Likert scales, where you go 1 through 5 or 1 through 3, and 90+% of the children, when you'd ask them questions like, does Marnie teach you to read? Is Marnie a sensitive and caring teacher? Does Marnie behave like a real teacher? They responded at the highest level, yes. They just are engaged with Marnie. And they didn't always just, it wasn't a Pollyanna effect. if you'd ask them, what do you think of Marnie's voice? And we have a lot of old recordings, and sometimes she sounds like Minnie Mouse, and sometimes she sounds like a real person. She said, her voice kind of sucked. So they were very honest, and when they really liked Marnie, they were giving us honest answers. They really liked Marnie as a teacher. Children are engaged with virtual characters, and there's a lot of research to be done to say what's the ideal character for a particular student. Okay, and I don't think one character serves all. So there's a lot of good research to do about that. Let's talk just for a minute about believability of characters. This is just a fun thing with about 10 slides that'll take a minute. If you look at what great learning experiences are, great communication, say what is it that happens? So first of all, communication is multimodal and expressive. I would argue it's multimodal even when you're talking on a telephone. Because you watch someone talking on the telephone, they smile, they nod their head, like the other person's there, right? You have a mental image of that person. We always move our mouth and face when we speak, and people use that information. There's about a 15 decibel advantage. The signal-to-noise ratio is better in noisy environments when you're looking at a person's face, even if you're not an expert speech reader. You use information about conversational exchange, so forth and so on. It's also interactive and emotional. You emote whenever you speak, and you're constantly exchanging verbal and nonverbal signals. You're always gesturing when you speak. Every culture gestures. It's always in synchrony with the speech, and more or less it's an expression. It's your own expression of what you're trying to say and putting it into a visual form. And it's very compelling. You'll be driving at 80 miles an hour with someone, and they're talking to you, and they look at you, and they take their hands off the wheel, and they start gesturing, right? So it's a very compelling thing and a very natural thing to do. So we want to put all of those features into our systems. Let's give an example here. I'm conversing with you, and you're an attractive female. I'm conversing with you, and I'm telling you something, and I receive this feedback, and then I receive this feedback, and then I receive this feedback, and then this one, and then this one, and then that one, okay? And thanks. This is from Erica Rosenberg. She's Paul Ekman's protege. Paul Ekman is retired. He's the world expert on expression of emotions through the face. And she teaches the courses on facial action coding now and gives those workshops. And she's a distinguished researcher, and we collaborate with her. And she gives us very good expressions and feedback on our own models. Now, what those expressions meant depends on the context. So if I was telling her this wonderful story, and she's going through these things, then it could be that she's being totally empathic, and I'm being a great storyteller, and she's responding exactly like I want. Or I could have been telling her an off-color joke, and she's going, why, you sexist pig, how could you possibly say that? I can't believe it, right? So it all depends on the context. But for characters to be believable, they have to produce good emotions, because that's part and parcel of speech. So what we did is we gave our characters that we thought we designed well from looking at pictures, okay, of people in different poses, and then she'd give us feedback, because she knew exactly how the muscles are supposed to move. And then here was the old one, here's the new. Does she look more angry here? They're very subtle differences, but she looks more angry. And then look at the disgust. The old one is not really very disgusted, more like angry maybe. The new one, she's really looking disgusted, okay? And she told us exactly how to do it. And we actually added wrinkles to the face and so that you can see the muscles moving, and did different texture maps based on what she told us. Here's the fear, old, new. I'm not going to give you time to read all the feedback, but you can just see the difference between the old and the new. You know, the eyes are wider, the eyebrows are a little higher, and look how much more afraid she looks. And then look at the surprise. Her eyebrows much higher. She looks much more surprised. So you need experts. Okay, look at her joy. Here looks like she might have been getting pinched rather than being happy, and here she's happy. So it's really important to get these kinds of things right, and there's a lot of work to be done at all levels if you're going to build effective learning tools. So what have I said so far about reading? I said there's a whole science about reading, and you want to use the science. There's a whole science about designing interfaces, and you need to use that science. There's experts, and in fact our Foundations to Literacy program, this is a good story, is based on, loosely, it's based on Linguistic Remedies, which is a tutoring system that a reading researcher created. Her name is Barbara Weiss, And I met Barbara Weiss because she's a PhD that came out of University of Colorado. And one of the teachers she taught to tutor taught my son, who was an off-the-scale dyslexic and who now reads books. So I believe in this stuff. And we modeled the expert, and we had an expert that knew about scientific reading. She didn't have a clue how to design interfaces. She wanted her characters to just go wrapping around, you know, talking like she does, and the kids would fall off the chair in boredom. You need a lot of interactivity. So you need expertise from lots of areas. You need our expertise about how to design the interfaces, and you negotiate and collaborate with these experts. So
what do you think about the similar kind of teaching, not just the reading, but maybe mathematics, maybe drawings, or maybe some other skills?
Coming to it. It's all about how do you go from teaching reading to learning. Now, obviously, some of the same principles are going to apply, but there's theories of comprehension. Like Walter Kinch is at University of Colorado, and he's one of the gurus of that. And it's how do you present information in a way that the people get the key ideas, and then they use their own knowledge to create new mental models, right? And constructivist learning, and then how do you assess and promote that comprehension? And we're going to talk about that, and that's what Wayne's going to talk about. So I'm going to spend very little time on this, because I was invited here mainly because of the education. But I want to say we have as much money in our lab right now for inventing virtual therapists as we do for inventing reading tutors. And we're building 4 different systems, and every one of them has already been built. And 3 of them are in clinical trials. So people are using these systems. Basically what happens is that distinguished researchers that have spent like 10 or more years in the laboratory, funded usually by National Institute of Health, have developed treatments that work. They've demonstrated efficacy. And what they have is a system that works in the laboratory and is intensive, and there's only a few people that know how to use it. So if you could build a computer system, millions of people would have access to it. So we build a virtual human that tries to model just what they do in the therapy. I'll go through one really quickly. Lee Silverman voice treatment. This was for Parkinson. 90% of people that have Parkinson's, and there's tens of millions around the world that have Parkinson's disease, have a speech or voice problem. And these are the qualities. They're hard to understand and hard to hear. They start speaking very soft, and they have a hoarse voice that's monotonic, it lacks emotion, doesn't reach the articulatory targets, and so forth. And what Lori Ramig realized is that rather than doing speech therapy, which was shown not to work, traditional speech therapy, she just taught people to think and speak loudly. And she would model that behavior. So people with Parkinson's would look like this and produce speech. She'd teach them to take a big breath, put their head back, mouth open, produce a big ah, and she'd measure their sound pressure level and give them lots of encouragement and teach them the right way to produce so it wasn't causing pain and discomfort. No hyperarticulation, hyperfunction they call it. So it had major impacts. Almost every patient benefits immensely from this therapy. And unlike most speech therapists, she went around the world and certified other clinicians, and there's about 2,000 certified LSVT clinicians now teaching people with Parkinson to communicate. And the problem is it's 16 hours of intensive treatment. So it's an hour a day. You can only have about 5 patients a month. Whereas with these systems, you could have thousands of patients a month. Okay? So these are the effects. They start out like this. After the month of therapy, they're twice as loud, about 12 dB louder. 2 years later, they're still twice. Well, they're still 4 times as loud. Now they're twice as loud, 2 years later. The main thing about this thing that was so amazing is that the people came alive. Their emotions were better, their face motility changed, their quality of life changed, their self-confidence. They had brain function changes. There's 3 or 4 studies have shown changes in brain function. They swallow better. It's been a wonderful thing. It's a set of different exercises. I can demo them after. I won't take the time to do it now. But this actually takes speech input and is giving real-time feedback. So Marnie says, okay, let's practice your loud ahs. And then I go, ah, and that car starts, and I want to keep it above the line. All right? And the white line is how far I went last time, and the blue line is my target. And as I'm getting there, she's smiling and saying, go, go, go. Okay? And just like they do in the therapy. And there's a set of these different kinds of exercises, and we implement these, and they're in clinical trials. And the first patient that used it 74-year-old Parkinson woman. She loved it. She said, but Marnie works me too hard. She's relentless. She really makes me work. Okay, so we also have 3 systems that we're building for people that have aphasia. Each of these is based on a laboratory treatment that works. These aphasias, a lot of trouble speaking, expressing themselves, usually from a stroke or from an accident, some kind of brain trauma. And we have 3 different systems we're working with different researchers. They're all funded by NIH exploratory research grants. And each of these has been developed or are going into clinical trials. So now I'm going to switch gears. I've explained our reading system. I've told you about how we've generalized it to another domain. I've given you the vision and some of the benefits, the accessibility and so forth. And now I'm going to just, in 10 minutes or so, we'll wrap all of this up, I expect. Huh? But I expect there'll want to be questions. So, okay, so 15 minutes at the max, because we can talk about the research challenges at the end if you'd like. So now what we have is, what you've seen here is systems that do combine state-of-the-art computer animation and speech recognition technology. The speech recognition in the systems I've shown you is limited to detecting the loudness in the therapy systems, to tracking the speech. So when the person in the LSVT is reading, and we want them to read loudly, we can follow them so we know that we're tracking what they're reading. When the students are reading out loud in books, we follow what they're reading. Okay? You saw that when we align the speech with the lips, we do that with the speech recognition system. At the end, I'll tell you about that animation system. I think the animation system with the lips is state-of-the-art, and it's an extremely sophisticated system. We went to Hollywood and did motion capture of all sequences of phonemes in English. And so we have motion capture data, and then we basically do like text-to-speech synthesis by concatenating these sequences of points. But it's a lot of equations because all you would be doing is moving one point. And in fact, you have to move all the points in a way that makes for graceful articulation. But we created this concatenative synthesis. You know, one day I'm standing there saying, geez, you know, we do this morphing and it sort of works and it isn't very natural. And Wayne Ward pipes in and says, why don't you do it like text-to-speech? And that started this project, and then we did a couple systems and ended up with the one we have today. So that's how things work at CSLR. Random guy that works in dialogue and information retrieval comes up and tells you how to do your animation system. That's what you love about being in academia. Okay, so our vision quest is to combine the work that Wayne and his group does. And Wayne has a group with Jim Martin and Dan Jurafsky, who won the MacArthur Genius Award, and Kadri Hasioglu, and who am I missing? Some students and himself. And they have grants from various agencies, NSF and DARPA and various defense agencies, to be able to ask questions and go to the web and get answers. Okay? So like Ask Jeeves, but much more sophisticated. The idea here is that what we want to do, this is to your general learning question, Lee, is what you'd like to be able to do is take a book and just scan that book in and be able to do everything automatically. So the book represents all of the key concepts and all the relationships between the concepts. You know, what was the catalyst, what was the cause, who did what to whom, and then at the proper times from parsing the books, questions are asked. And then based on what the response, the explanation the student gives, and the knowledge you have about the relationships in the book, you know what they know and they don't know. And then you ask questions just like you would do with a Socratic or tutorial dialogue that leads the person to discovery. And that's the vision for the future. And that we've actually made proposals like this to the NSF and to the NIH, and there's one pending now to Institute for Educational Sciences. And I'm going to turn it over to Wayne now, and he can tell you a bit about the technologies that underlie the ability to parse text so you can capture these relationships. And our vision is to have a tutor like Marnie, or maybe they'd look more like Einstein or whatever, depending on the topic, having these dialogues based on this automatic gathering and representation of knowledge.
Unfortunately, there's a big gap between
Turn mine off, right?
proposals and funding. What? I said there's a big gap between writing the proposals and having them funded and getting them. So, yes, we're writing lots of proposals on this. Like Ron said, our longer-term goal is to automate this as much as possible, to reduce as much as possible what you have to do to author a new lesson plan, particularly if you're trying to teach not reading, but science or math or conceptual. So our long-term goal is to represent all the items in the text that's necessary to do these tasks, and boiling down to entities, events, roles, the relations between entities and events and between events, and temporal aspects of things, and use these as the basis for tutorial dialogues. That's a lot to do in an ambitious project, so we're, in taking it one step at a time, have a more immediate goal, which is to move from a domain-specific representation that we use now, and that in fact most people use now, to a domain-independent one, so that the representation doesn't need data or rules specific to each domain. So you can train it up from general data and then not have to go put a lot of work into each new domain. But it also has to be specific enough to be the basis for tutorial dialogues within a specific domain. And to be a basis for a tutorial dialogue, one thing it has to be able to do, I spelled that wrong, is assess the quality of answers. You're asking a question, the student gives you an answer, it's unlikely it's going to exactly match the answer you were expecting, so did they get it right or not? Or if they didn't get it right, how do you ask them follow-on questions to elicit the right answer? Because our goal here isn't really to score a student and say, you got it wrong. It's to help them get it right. And we have to be able to generate clarification and verification questions along that line. What if the system doesn't know if they got it right? It's not terrible. It can always ask them follow-up questions. So an example of a domain-specific representation that we would use now, or you have frames specific to a domain and frame elements, pieces of information that, again, are very specific to a domain. So I know a lot of you know and love the air travel domain. So, for example, you might have a frame about air travel that has an origin that's a city, and a destination that's a city, and a travel date that's the name of a day, and a period that's like morning. So I want to go from Boston to Denver on Tuesday morning. These systems can actually work very well. But the problem is you have to have a limited enough domain that you can actually enumerate all the important concepts, and you have to put enough work into it to put the domain-specific representation there. And it can be quite a lot of work. What we're trying to do is to use domain-independent shallow semantic annotations. And as Ron alluded to, we're trying to use the work that we're doing in other projects. So in particular, we're funded for doing semantic annotation for open domain question answering under the R2Acquaint project and an NSF ITR. What this means is a person comes up and asks you any question about anything, and you're supposed to retrieve the documents, say using Google, and rank order the answers, and then extract the correct answer rather than pointing you to a set of documents. When you're dealing with really huge amounts of information and huge numbers of documents, you can't really sit down and write any sort of domain-specific representations for these. So we use a number of representations. One, typically called predicate argument structure, where you, for each predicate in a sentence, mark what the semantic roles of its arguments are. If there are any of you that are into this sort of techie thing, there are a couple of corpora that are annotated for this purpose. One is prop bank, one is FrameNet. We also use other corpora to annotate entities, events, and temporal expressions. So there's a program called ACE that's in the past had corpora for annotating entities, entity mentions, and aggregating those into complex entities. And ACE now, this year, is also moving on to events, where they actually annotate events, where you're supposed to find all the event mentions and do co-reference between those event mentions to say which of those are in fact the same event. There's another corpora that marks up events called Time Bank. And NIST holds an annual turn competition, which is for finding temporal expressions. Right now, I should mention, we do all of this in English and in Chinese. So semantic role labeling is essentially for each predicate in a sentence, and a predicate doesn't have to be a verb, it can be a nominalization or even an adjective. You assign labels to sentence elements that play roles with respect to that predicate. So the general idea is to try and represent who did what to whom and when, where, why, and how, although not necessarily with those labels. So here's an example. Bell Atlantic Corporation said it will acquire one of Controlled Data Corporation's computer maintenance businesses. Said and acquire are the two predicates that we annotated here. So for the first predicate, said, the who is Bell Atlantic Corporation. The what it said was it will acquire one of Controlled Data Corporation's computer maintenance businesses. For the acquire predicate, the who is it, and you have to do the co-reference to realize the it's talking about Bell Atlantic Corporation. And what it's acquiring is one of Controlled Data Corporation's computer maintenance businesses. So this is just the notion of a very shallow, for each predicate in the sentence, what roles are it playing. So who did what to whom and when and where. So some examples from Prop Bank. I won't go through these in any level of detail. Prop Bank uses a very non-mnemonic general purpose labeling scheme. So for the predicate acquired, generally the arg0 is the subject of a transitive verb. Sony Corporation did the acquiring here. What was acquired is Columbia Pictures. FrameNet uses a very different sort of representation that has frames and frame elements specific to those frames. So the roles played relative to the predicate change with each frame. So for example, FrameNet would have a frame getting, and it would have the roles time, recipient, and theme. On June 8th, Caparo began to acquire Fidelity shares. It would have frames for judgment, where you have an evaluee and a degree and a cognizer, and one of the targets for that frame would be valued. It would have statement frames, where there's a message and a speaker, and an example of a predicate that invokes that frame is said. So both Prop Bank and FrameNet are corpora that are built by hand. Prop Bank was done at UPenn and FrameNet's done at Berkeley. And they're both ongoing projects. The idea behind this is it gives data for people to train systems, if like us you use machine learning sorts of classifiers, and to evaluate your systems, and hopefully to transfer them to real tasks. There's another level of representation that's sort of intermediate between those two, more general than FrameNet and more specific than Prop Bank, generally called thematic roles. And thematic roles are things like agent, theme, means, and cause. Everybody has their own set of thematic roles, but generally people settle on roughly about 20 of them, and there's a large overlap. So there is no corpora actually annotated with thematic roles, but you can map from the existing corpora, FrameNet and Prop Bank, to thematic roles. And an example of a thematic role assignment would be John Wilkes Booth is an agent, assassinated as a predicate, Abraham Lincoln is a theme, and In Ford's Theater is a location. So you can see once again a who did what to whom, and what are the roles relative to each of the predicates.
So any of these representatives can express the conditional, sentence. If something happens, then something happens. Which one of those will do that?
So none of these specifically represent a conditional. That's represented externally to the predicate arguments themselves, right? So there is another, so if he said this, then he did that. You have said and did, and you'd have your relationships there. The hypothetical or the conditional is on top of that. It's important, but it's not the roles being played relative to the predicates. So we'll get, a little later on, we'll get to that. So the roles relative to the predicates just say, well, there's a said event. What are the players? There's a did event. What are the players? It's inference on top of that you're really talking about, right?
I think for educational application, you really, if you want to teach children how to learn, do inference,
Yes,
and
yes.
that's how it's pretty.
So, but what I'm talking about here is one level below inference. You produce a representation that you then perform inference on, right? We do, in fact, have systems that do the semantic role labeling. And in order to do that, what we do are to extract domain-independent features from the input, like is the particular set of words we're classifying before or after the predicate? Is it a passive or an active sentence? We have two systems. One is based on a full syntactic parse. You can get from a Charniak parser or a Collins parser. This system is more accurate, it's more precise, but it also requires that you be able to get a syntactic parse out of it. So, for example, it does not work so well on word lattices or outputs from a speech recognizer or for conversational speech. It works very well for expository text. We have a chunked parser, which basically takes a support vector machine, chunks it up into a flat syntactic representation, and then does semantic classification on top of that. That's much more robust. It actually works very well on output from a speech recognizer. It is fast enough to run on word lattices. It isn't bothered very much by the disfluencies in conversational speech. Our general technique is to annotate data, or hopefully to get annotated data, and then just train machine learning classifiers to assign these roles. If you're into this sort of thing, the particular classifier we use is support vector machines. Doesn't matter a great deal. What matters are the features and the data. Any type of machine learning classifier will do a pretty good job on this. And then the roles are assigned to the constituents of the pars, or the chunks in the chunked representation. Right now, our performance is about 81% per precision and recall for an overall F-score of 81. So this just gives you an idea of how well the system works. And this is on real input. So what would we do with thematic roles like this if we could in fact produce them? So an example of how we would try to use this is to look at thematic roles in a reference answer and the thematic roles in a hypothesized answer and be able to judge the goodness of the answer. So for example, techniques we use now like keyword spotting or latent semantic analysis are good at figuring out if you've got all the right words in there, or if you've got words that are sort of all right, it does not represent at all the relationships. So you can have all the right words and the whole wrong concept, and it wouldn't be able to tell you that. So for example, we actually had a kid's story about a dog, Racer. Racer had problems with his back legs. So that would boil down to you've got the predicate problems, the agent is Racer, and the theme is his back legs. Fang bit Racer and ran away faster than Racer. For the predicate bit, Fang is the agent and Racer is the theme. For the predicate ran, Fang is the agent and faster than Racer is the role respective to that. I just called it adverbial. And so this gives us a way of comparing answers in more detail. So if you have a reference point, Racer had problems with his back legs, and you had an extracted sentence from a summary, Racer got his leg hurt. Well, does that mean the same thing or not? And if not, what can you do about it? So the answer here is what this allows you to do is analyze the two in more detail. You can compare the predicates. You can compare the roles and the entities filling those roles. So you have two predicates, problems and hurt. Racer's the agent on both. Hey, that's good. The same roles, the same entity filling the roles. You've got theme, back legs and leg. Well, are back legs and legs the same thing or not? Is problems and hurt really the same thing or not? What it does is give you a way to find out exactly what the differences are so you can, in fact, ask questions about them. We do have, in fact, ways of looking at the semantic similarity of entities and predicates. We do, everyone else does too. So here's another example. So, as I mentioned before, the predicates and their roles are one of the mechanisms we're looking at using. Another is to annotate entities, events, and temporals and actually build a more complete representation of what's in the text. So this is a little bit of an involved example, and I'm going to run it through it really quickly. If you're interested, come talk to me later. But the idea is, with our various taggers, we tag all the entities, and we tag the events, and then we try to also assign the relations between them. So in this sentence, this is an example from our question answering system where the question is, how did Sadat's assassin die? Where you don't know what the assassin's name is. And much of the problems with things like this in question answering are if you just look at Sadat and assassin and die, you have lots of false positives because there are lots and lots of articles about how Sadat in his earlier days was going to assassinate someone else. And you must know the roles, that Sadat's the one being assassinated and you want the person that assassinated him and how he died. So regular bag of words techniques don't suffice here. So in identifying the entities, the Islambuli Brigades is named after Khaled Islambuli, the leader of a group of militant Islamists who assassinated Sadat during a 1981 military parade in Cairo. So if you extract all the entities, that's represented by the boxes down bottom here. You have an entity mentioned, Islambuli Brigades, that's an organization, brigades. A group of militant Islamists and WHO are both an organization. Cairo is a location. So it first goes through and just extracts all of the entity mentions and aggregates those into a set of specific entities. We then annotate the events and the relations between them. So for the same general question here, Islambuli and 4 associates were captured and executed for the plot to kill Sadat, which was carried out by Egyptian Islamic Jihad and another Egyptian militant group, whatever. So you can see, without going into too much detail, the sort of representation that we produce here. The boxes are the entities, the ovals are the events, and the labeled arcs between them are the relations. So there's an executed event whose reason was a plot event. There's an assassinated event. The killer was the Islamist. The victim is Sadat. So you can see this is a much more specific sort of representation, and our general notion was, well, hey, if we can ask, if we're using this to answer questions, we can use the exact sort of dialogue, use the exact sort of representation in a dialogue to try to both ask and answer questions in an interactive session with students. So the idea in our immediate task is, how do we go from a knowledge representation like that to dialogue models? So right now, our dialogues generally consist of a form-filling paradigm with manually constructed frames and frame elements. An example is our communicator system. An example is almost anybody's domain-specific system that actually operates well these days. You represent specific information about a domain, and the system tries to essentially use a form-filling paradigm to go find out that information. What we hope is the automatic generation of dialogue from knowledge structures that represent the events and the entities and the relations. As a very quick example of what such a thing would look like, there's a tutorial text that we dug up off of the web from, I don't even remember where, Department of Ed's website, on dental hygiene. And it goes through a little text explaining to kids why it is you should brush your teeth and about plaque and bacteria and cavities. And so the idea here is the instructor would then say, here are the important points I want the person to have learned about this lesson. Brushing your teeth removes plaque and reduces bacteria. Bacteria produce plaque. Bacteria produce acid. Plaque traps food for bacteria. Plaque holds acid against the teeth. Acid can eat holes in the teeth. So basically, here's what the instructor wants the child to know. So we would try and take this, represent this as a knowledge structure, and then interact with the child to ask questions about it and determine, do they in fact know those points? And an example of how that might go, we have the reference point for brushing your teeth removes plaque and reduces bacteria. So the question would be, why does brushing your teeth help stop cavities? An answer might be, it gets rid of the bacteria. In addition to bacteria, what else is removed? Don't know. Here it's looking for the reference, plaque. What is the gluey stuff that bacteria produce? They give the answer, acid. Once again, it's looking for plaque. So then it gets a little more specific. Is the gluey stuff acid or plaque? And then they say plaque. So the idea is it's trying to reproduce the structure that it's built, and it's asking about the specific part of it that's either missing or wrong, and it gets successively more specific in the question that it's asking. Give it back to Ron.
Okay. Can you hear me, Brian? Let me give you some perspective here. I give a very high-level talk about various technologies and how they're used. Okay? Wayne's talk went a little bit lifting up the hood. But everything I talked about had an equally detailed structure underneath it, right? And if you take what Wayne just said and bring it up to the high level, there's your competitive advantage over Google. There's your future of asking any question and getting an answer and having Einstein come on or your character be the perfect assistant or tutor. Or taking any book and automatically generating a tutorial dialogue for learning. I mean, this is really the future. And I really think it was good to have this contrast between how the things work and just seeing the high-level technology. It would have taken a whole-day workshop to do both of them at the same time. All right? So you can see what a wonderful, it's a kind of a match made in heaven here between people that really work on the recognition and machine perception technologies and can build these virtual human systems today, and the systems that are going to create the knowledge representations and the dialogues for very high-level comprehension training in the future. So one of the things we can do today, which is kind of cute, is you can test virtual human systems in real time using a kind of Turing test paradigm. I can wire you up and use computer vision algorithms like a company called Face-to-Face with Eric Pettijohn. If you take a high-quality video, they can then use their processing to produce in near real time talking face that an animated character that's producing just what your face did. So it'll track all your movements and so forth, and then map them to a model and do it in real time. So imagine me with a bodysuit, like doing motion capture, like when they do Shrek or something, and with this algorithm that produces the face, and you have me behind a screen being a virtual teacher, and the character is interacting with me, but it's really me behind the screen controlling the teacher. So you've got the expert teacher controlling the animated character. So is it live or is it Memorex? Was it artificial intelligence in my completely automatic system, or was it a virtual teacher? And you could evaluate them this way. That's just a thought for you, okay? We don't actually do that. It's just too expensive. What we really do is clinical trials, where you look at how well did the child do when you put this computer treatment versus how well did they do in a control room where you have the teacher doing the normal instructional method, okay? And we could talk about evaluation, Margaret, and when you get these things into the schools, because a very interesting and complex issue about how do you assess technology in classrooms. what NIH and Department of Education really wants you to do is just like a clinical trial, where you do random assignment of the students in the classroom to a treatment and control condition. The problem with that is there's something called compensatory response to treatment. And what it is the teacher says, that piece of software isn't going to beat me. And they watch just what's happening with the teachers. And we've seen this. We did random assignment in a Catholic school, and it was wonderful. The nun was just the best teacher in the world. And she went after school and went into our managed learning environment and looked at exactly the progress of each child that was in the treatment, and then gave that same attention to bring the other kids up to it. And that's been observed in other places too. So that's why we go and we do quasi-experimental design and put the classroom controls in one room and the treatment in another. Okay? So it's complicated. This is so different than a clinical trial. Was it a placebo? Was it a regular pill? The experimenters don't know. You know, only the evaluator knows, and they know after the fact, and so forth and so on. So it's a different thing. So it's noon. I can stop now, or we could just vacate the room except for the techies who want to look at the 5 minutes of technical challenges. You can tell me what to do. Go for 5 minutes?
Well,
what do you want to do?
Give you a round of applause for this. If people want to stay, you're welcome to.
Yeah, I think the room is open.
Okay. So all we're going to do here is something very simple. We're just going to go through really quickly and tell you about the technologies that were in the virtual therapy systems today, and then talk about what the challenges are for tomorrow. It's very, very superficial. If you look at machine learning and machine perception, which is what's driving these characters, then you can look at it in the auditory modality and the visual modality, and you look at it in terms of the input, the recognition and understanding, and the generation and synthesis. So take a matrix like visual recognition. This is interpreting the mouth movements, the face expressions, the gestures, and so forth, and combining that with the auditory signal to get a richer representation. If you're talking about the generation synthesis, and with the animated characters, we'd like them to produce natural emotions, natural head movements, and gestures fully automatically, given just text and or speech. Okay? We haven't talked much about language generation, and I don't know a whole lot about this area, to be honest. Wayne is the dialogue builder, but pretty much we build templates for answers and can paste the words in and do synthesis that way. It's not very sophisticated what we're doing today. I have read papers where people talk about sophisticated models with AI, but we don't use those in ours. So in the face animation, our current solution is this concatenative synthesis and a few rules. I thought I had a better slide on that. So here's what we did. So this was in a Hollywood motion capture studio. This is a very good sport. This happens to be Barb Weiss, our reading researcher, who designed the Linguistic Remedies program. She's a distinguished researcher, but she also feels like she knows just how she wants the words to look when she says them, because she talks to the kids all the time. So she agreed to go to Hollywood with us, and we put her and put all these dots on her face, and then she would say the different words. And a system would be capturing each of the X, Y, Z coordinates in space at 30 frames a second, okay? And then we would use those in the concatenative system. Here's the thing. So a second thing we want to do is to be able to generate head movements, facial expressions automatically from text and or speech. What I told you we did is a few simple rules, okay? But imagine building a system that's just like what you do with your HMMs. So you have features that you extract from the signal, and you have a corpus of annotated data. So what would that annotated data look like? Well, there's facial action parameters, which are the MPEG-4 standard. And like I said, face-to-face, you can take a video of a person talking, narrating a book, or being in a conversation, and then you can generate 30 times a second these facial action parameters. Those are like the points on the face, and there's a set of points that tell you how to move in the 3 dimensions to change the dynamics of the model. Okay? So if you had a corpus of facial action parameters, and you had the speech, and you said, okay, here's the words, and here's the pitch periods, and here's the semantic features like Wayne just said, and you input those into a support vector machine or any other kind of classifier or modeler, you could predict those parameters and drive the face. So you have the basic concept of a statistical model for taking text and speech, putting in all that knowledge about the features of the speech and the text, and then trying to produce the facial action parameters. In fact, what we proposed to the National Science Foundation, we haven't heard back on this yet, is that on top of the facial action parameters, you do the facial action coding scheme, which gives you the movements of the muscles. And then you can learn that relationship and have a higher level conceptual categories that you want to recognize, like you did this emotion or lifted an eyebrow and so forth. So there's a concept for you for research to do that, and that's the future. Spoken dialogues. Our CU communicator system did an extremely good job. It had like 95% task completion. You'd call up the system, independent evaluators, and they would make travel plans in the US or also internationally. I can't even remember. International travel plans. You could book hotels and rent a car, and it would send you an itinerary. Had over 95% completion rate and very high user satisfaction. It was actually the best in show system the last 2 years of the DARPA communicator program. The problem with these systems is that they're manually built. Even though you have statistical training of things, you decide on the ontology and the frames, and you build the grammars, and then you train them. You do Wizard of Oz studies first to do this, and then you put the system in the field, and you do tests, and you increase the coverage, and you retrain it, and you engineer it, and it's a lot of work. The only reason people in the speech companies aren't making money is how much work it takes to build these systems. They work just fine. You call Tell Me or you call United Airlines, you use an automated system, and you get information, right? But the cost is more than the return. So they're down to a couple of companies now, right? So the there's what?
I said they merged down to one.
There's down to one that I know of. Well, you can call IBM and Microsoft and Scansoft. Any others? I don't know any others anymore. Okay, so anyway, the proposed work, and you saw some of this from Wayne, is to figure out, using knowledge representations, how you generate these dialogues. And you compare answers using these form-filling models to the representations, and you decide, probably based on data and lots of examples from domain-independent texts, if they got the right answer or if you want to ask another question and so forth to lead to discovery. And you need to come up with the notion of a story map, like what is the sequence and the relations they have to understand to follow that sequence to show understanding. And you guide them toward that resolution. And a lot of unanswered questions there. It's not like we say we know exactly how to do it. What we say is, give us money to explore this space, and we'll do it for some domains and learn the principles and build tools, and other people can do it. What we have done through our careers, Wayne and I, is provide tools and corpora for other people to be able to do research. Microsoft, when Shui Dong was running the show here, funded us for several corpora at OGI, which we then gave to you and then distributed to the world. So we always feel an investment of us benefits the community because we share everything we do through community resources. Speech recognition, you can come up here and say this better than me. I used to be a speech recognition researcher. Wayne still is, and Brian Pelham is at our lab. But basically, speech systems work to the extent that they're trained and the training data matches the test data. I mean, that's pretty much what you can say with some machine learning in there. And what you really want to do in the future is figure out how you can put systems out there that don't require all of this annotation and retraining and so forth. Because I can walk into a new room with new people with a foreign accent, and they can talk to me about something I never heard before, and I understand what they're saying usually when I have my hearing aids in. So, you know, that's how our systems have to work. We have to figure out how to have general purpose systems. And I don't have any solutions for that, really. And it's a good topic for discussion, but it's way different than what we do now. We have good systems for our domains of children reading aloud. What we do is we have a general purpose speaker independent recognizer trained on children's models. And then when we go into a book, we take the language models from the book and mix them up with the general purpose language models, and the sequences of words then help constrain the recognition. Okay? And of course, we know what they're reading and where they're reading in the book, so it's a highly constrained problem, and we can do quite well. Computer vision, I've worked with 2 or 3 leaders in the field in research labs, and they produced impressive laboratory demos, but they were never robust enough to be used in our systems in the schools. We could play with them in the labs and show demos. They're systems that can recognize emotions quite well. They're systems that can track where your face is quite robustly. They're systems that can track where you're looking. Putting this all together is not something that I've seen yet as something that can be done. And then what happens is you put things in a system like we could know where the person's face was. Okay? Now you want Marnie to do something believable knowing where the person's face is. So Marnie has to orient to the person in a realistic manner. Unsolved problem. You'd think it was simple. Just move Marnie's head. Well, that's not what happens. If I move over here, I see more of the side of your face. And there's parallax, and this is moving faster than what's behind. Marnie just moves her head. What happens is you think she's looking over there, and you don't get any of those cues, and it doesn't look realistic at all. And then you have Mona Lisa effects, where the eyes are looking out, and so forth. We were unable to solve those problems in the period of time we had, and then the funding went away to do the computer vision. So I would say there's great work, great potential. You have to have computer vision to have this realistic face-to-face dialogue with the character, and it's a wonderful area for research and integration. You got to have it, and it's not quite there yet, but it's almost there. That's pretty vague, sorry, but I just say this is an area to invest in. Okay? Hey, we reached the end of the show. Click to exit. Thank you so much. You're a great audience. And thank you for coming and being on the left side. You anchored me.
I was on the web before. Used to be able to put the web people over there.
That center of mass moved more toward the center.
Yes, it did.
Totally tangential. You mentioned that black students like to have a black teacher in Are you familiar with Mavis Beacon?
No.